This is a continuation of the previous video. We were taking the time to explore the cubes inside the synergetic tin because this was my first breakthrough in understanding how building physical models of fundamental structures are instrumental in finding the constants that interconnect essential parts into one whole system, synergy. The previous videos have demonstrated the advantages digital models possess in explaining these connections. I would build a physical model, photograph it, and send it to Fabiano Schwabi in Brazil, where he would make a digital version of it. The three landmarks we always used allowed us to always orient each new structure in the same location position as all the others. Let's focus now on the cubes inside the four systems of the bubble family, the fivefold symmetries. In this case, their size will fit exactly inside the 6BB VE, which equals 12 centimeters edge. We learned that the long axis of the bubble diamond of the triaconta is connected to the square face of the VE. Multiply the long axis of the square, corner to corner, by GR, and you have the long axis of the bubble diamond, the long axis of the dodeca's pentagon, and the edge of the icosa. That measurement is the square root of 2 GR 6BB. That also is the measurement of the edge of the cube that fits inside the 30-sided triacontahedron on the left and the 12-sided dodecahedron next to it. This relationship is constant and self-organizing. If you know one, you know them all. The 8 corners of the cube correspond to the 8 blue directions radiating out from the center of any structure in the sphere family. The second cube is smaller, that fits inside the icosa and the icosidodeca. This cube is connected with the octahedron that surrounds the icosa. Buckminster Fuller discovered the S module, the symmetrical modular unit that converts any icosa into an octa. There are 6 units that are easily reproduced. Because we always use an axis of spin, there is a handedness, clockwise and counterclockwise, alternating from side to side. Here you can see 4 triangles of the larger octa. The top triangle is spinning in clockwise. The triangle to the left is counterclockwise, and if you follow the other triangles, you can see they alternate between the 2 spins. Looking for handedness will prove important in building physical models of fundamental structures. A cube that fits inside an octa is the same as the icosa's cube in this case. We know the edge of the icosa is the square root of 2 GR 6BB equals 10.4 ... The edge of the octa is divided by the standard GR squared division to fit around the icosa. There is a numerical constant that will tune any octa around an icosa. That number is the square root of 2 GR squared. Because the number is less than 1, we divide the edge to make it bigger. Icosa edge divided by square root of 2 GR squared equals 19.41 ... We know from the previous video that the numerical constant that fits a cube inside an octa is the square root of 2/9. If you multiply the edge of the large octa by 2/9, you get a cube edge of 9.15 ... The bubble family has 20 blue directions radiating out from the center. There are 8 that correspond to the corners of the cube and 6 sets of 2 that pass through the centers of the other triangles. These are the base triangles of the S modules. This will prove useful in understanding how to build a number of physical models in the bubble family. This cube is the same for the icosidodeca, which is the interior structure that is the platform for forming either an icosa or a dodeca. There is a modularity to the essential parts of basic geometry. On the pentagons, you can place icosa caps to form an icosa. On the triangles, you can place a dodeca cap to form dodecas. This is the essence of what I mean by the term structural memory. Fundamental structures remember what worked in the past. Modularity and synergy goes hand in hand. I can show you a physical model of this memory by dividing the volume difference between the cube that fits inside the triaconta and the four systems of the bubble family. There are 6 modular units that define this volume. Each unit has a triaconta outer shell. These modular units show the relationship of the shapes of the different structures to the triaconta. Self-organization grows out of this remembering how shapes fit together. The first one defines the smallest modular unit of the bubble family, the T module. The orange 90-degree triangles on the outside surface are connected to the triaconta center, constructing the smallest synergetic volume in the bubble family. The next unit is the icosa by itself. You can see a little of the cube edge sticks out from this unit. This reflects the smaller cube inside the icosa. Notice there are many lines of communication connecting essential locations. The fourth unit is the dodeca. It shows the close relationship the dodeca has with the triaconta and their shared cube inside. The long axis division of the pentagons is simplicity itself in defining modular units. The last is the innermost system, the icosidodeca. There are 6 locations in common that connect the icosidodeca with the triaconta. They are defined by the 6 green directions in the sphere family. In the bubble family, these 6 expand to 30, passing through the 30 bubble diamonds that construct the triaconta. To the best of my knowledge, this 30-sided system has the most shapes that are the same of any structure found in nature, a limit case. By focusing in on the cubes inside fundamental structures, I discovered a whole new world of synergetic modularity. There are self-organizing building patterns that use a small set of structural and numerical constants that tie everything together. These constants build communication networks that interconnect the essential parts of fundamental structure into one synergetic whole.